We just held a piece of the sun on Earth for 6 minutes. And it didn't melt the machine. For 70 years, fusion energy was a magic trick that lasted milliseconds. A blink and you miss it. In 2025, the dummiest reactor in France turned that trick into a reality. Sustained, stable. Hotter than the solar core. Forget the headlines about net energy gain from lasers. That was a spark. This is the fire. If we can hold this reaction for 6 minutes, we can hold it forever. The math allows it. This is the end of fossil fuels. The end of scarcity. The beginning of the age of fusion. Imagine a glass of water having the same energy potential as a barrel of oil. That is the promise. But putting a star in a jar usually has one outcome: the jar melts. Or the star dies. So how did the team at WST achieve the impossible? They changed the walls. But inside that reactor, during those 6 minutes, something strange happened to the tungsten tiles. A phenomenon that nearly killed the experiment before it reached the record. You won't believe how they kept it alive. So we have to go back to the beginning. The world runs on fire. Coal, gas, oil. We burn things to boil water to spin magnets. It's messy. It's finite. And it's cooking the planet. We are desperate for an alternative. Solar and wind are great, but the sun sets and the wind stops. We need baseload power. Nuclear fission is the current answer. But it leaves waste that stays toxic for 10,000 years. Fusion is the opposite. It slams atoms together instead of splitting them. No meltdown risk. No long-term waste. It is the engine of the universe. Every star you see is a fusion reactor. But recreating that on Earth is arguably the hardest engineering challenge in human history. The villain isn't physics. It's heat. 150 million degrees Celsius. 10 times hotter than the sun. There is no material in the known universe that can touch that plasma without vaporizing. We've tried magnetic bottles since the 1950s. The tokamak, a Russian donut of death. We built JT in the UK, TFTR in Princeton. They all worked, for seconds. The plasma is like a snake. It twists, it fights the magnets, and it crashes into the walls. When it crashes, it cools down instantly. The reaction dies. The star goes out. For decades, fusion has been the technology of tomorrow. A running joke in science. Billions of dollars burned. Careers ended. The skeptics said it was a fantasy, until the team at the CEA in France decided to change the recipe. Specifically, the ingredients of the wall. Meet Waliest, the tungsten environment in steady-state tokamak. It's not the biggest reactor. It's not the newest. But it's the testbed for the giant ITR. The engineers at WST aren't trying to make power. They are trying to make the machine survive. Most reactors use carbon walls. Carbon handles heat well. But it sucks up the fuel. It retains tritium. That's a deal breaker. You can't run a power plant if the walls eat your fuel. So WST switched to tungsten. Element 74. The metal with the highest melting point of all. Tungsten is brutal. It's brittle. If you look at it wrong, it cracks. But it doesn't eat the fuel. The theory was simple. If we line the reactor with tungsten, we can run it continuously. But tungsten hates thermal shock, and plasma is pure thermal chaos. The 2025 campaign began with high anxiety. They were pushing the duration longer than ever before. They fired up the injectors. The plasma formed. The clock started ticking. 1 minute, 2 minutes. The heat load on the diverter was immense. Usually, this is where the copper cooling pipes melt, or the plasma collapses. But WST held. The magnetic control systems made 1,000 adjustments per second. Think of it like balancing a broom on your hand. You have to constantly move to keep it upright. The magnets are the hand. The plasma is the broom. The AI is the brain. At the 6-minute mark, the energy input was huge. 115 gigajoules. That is 15% more energy than the previous record. It sounds small, but in physics it's a chasm. They proved tungsten works. They proved the cooling works. The champagne was ready to pop. The data looked perfect. Until they looked closer. Sensors picked up a spike. X-rays. Something was happening on the wall. Tungsten impurities. Atoms of metal were flying off the wall. If tungsten gets into the core, it cools the plasma instantly. It's called a radiative collapse. The death of the star. The team had to throttle the power. They were walking a tightrope. Too much heat, melt the wall. Too little heat, the plasma dies. This is the tungsten curse. It survives the heat, but it poisons the reaction. They realized the standard magnetic shape wasn't enough. They needed a new configuration, an X-point radiator. Divert the heat, flush the impurities, keep the core pure. It was a gamble. Changing the magnetic shape mid-run is risky. If they lost control, the plasma would slam into the wall. Game over. They adjusted the field. The impurities flushed out, the core brightened. The temperature stabilized 50 million degrees. Steady as a rock, they crossed the 1,000 second mark. Then 1,200. Then 1,300. 6 minutes. In the world of fusion, that is an eternity. They proved the tungsten curse can be broken. Now let's see how. Let's look under the hood. How do you hold 50 million degrees in a metal box? The secret is that the plasma never actually touches the wall. It is held in a magnetic cage. Superconducting coils create a field stronger than a car crusher. The plasma is made of ions. Ions are charged. They have to follow the magnetic lines. It spirals. Around and around, a never-ending donut, the torus. But plasma is messy. It has turbulence. Like smoke rising from a cigarette. When it gets turbulent, it spits out energy. These are called ELMs, edge-localized modes. Think of ELMs like water splashing out of a bucket you are swinging. If that water hits the tungsten, it damages it. Over time, the wall melts. Stop. If you think you understand this, look at this number: 10 megawatts per square meter. That is the heat load on the diverter. It is the same as the nozzle of a rocket ship at liftoff, but a rocket flies for minutes. A fusion plant must run for years. Must uses active cooling, water flowing through the tungsten at high pressure. It creates a temperature gradient. 2,000 degrees on the face, 100 degrees on the back. This gradient creates massive stress. The metal wants to tear itself apart. Must proved that the new tile design can handle this stress, repeatedly, reliably. They essentially built a spaceship heat shield that never lands. This data is now being fed directly to ITR. The giant reactor being built next door. ITR needs to run for 400 seconds. Woyest just did 3 times that. We have the durability. We have the time now. What does this actually mean for us? This isn't just about boiling water. It's about energy density. 1 kilogram of fusion fuel equals 10 million kilograms of fossil fuel. A bathtub of water and the lithium from a laptop battery. That could power your entire life. Your house, your car, your food. For 30 years, and the waste, it's helium. The stuff we put in party balloons. But the Miesta record unlocks something else. Space travel. Chemical rockets are too slow for Mars. We need sustained thrust. If we can keep plasma stable for minutes, we can keep it stable for months. WEST just proved the engine for the solar system is viable. We are talking about a civilization level shift. A Type 1 civilization. 6 minutes doesn't sound long. But the Wright brothers' first flight was 12 seconds. Once you prove it can fly, it's only a matter of time before you cross the ocean. WEST just proved the fusion plane can fly infinite. Clean. Safe. The Holy Grail is no longer a myth. But, before you sell your oil stocks, we need to talk about the catch. Fusion has a fuel problem. We need tritium. Tritium is incredibly rare. There is less than 20 kT of it in the entire world. It costs 30,000 per gram. It is the most expensive substance on Earth. We have to breed it. We have to use the reactor to make its own fuel. This technology, tritium breeding, has never been proven at scale. Then there is the cost. WEST is small. ITR costs 20 billion. Critics say wind and solar are here now. Why spend billions on a gamble? Is fusion a distraction, a vanity project for physicists? The answer lies in density. Solar needs land, lots of it. Fusion fits in a building. It saves nature by not covering it. And regarding tritium, WEST is testing the blankets right now. The risk is high. But the reward is a planet that heals. For the people working at WEST, this isn't abstract. It's personal. Imagine spending 20 years on a machine that never worked for more than a second. The frustration, the funding cuts, the jokes. Then, the screen lights up. 1,000 seconds. Fun 300 seconds. Tears in the control room. Not of sadness, but of relief. Before Mullist, we hoped fusion was possible. After Bust, we know fusion is an engineering chart. It's no longer if, it's when. We have captured the fire of the gods. And we didn't burn our hands. So look forward 2035. The first pilot plants turn on. The grid stabilizes. Energy prices drop to near zero. Desalination plants run 24/7, turning oceans into drinking water. Carbon capture machines suck CO2 from the air powered by the star. Energy is the currency of life. When it becomes infinite, humanity changes. We stop fighting over resources. We start exploring. WEST was just a metal box in France. But it might be the box that saved the world. 6 minutes of eternity. Next stop, forever. This video took 100 hours to research because fusion physics is hard. If you want us to cover the tritium crisis in depth, comment fuel below. Next time we look at the anti-matter engine. Yes, it's real. If you enjoy videos that go deeper than headlines and actually explain how the world works, you're in the right place. Subscribe to the channel so you don't miss the next breakdown. Hit like if this video helped you see something differently. And if you have a question or a topic you want explored next, drop it in the comments. Your curiosity drives this channel.